Hello, everybody, and welcome to another Saturday discussion brought to you by CodeNewbie.com, the place where code newbies, pros, and programmers of all kinds can get together, talk about their code, talk about the things that they're doing, and talk about life in general. This week, I actually have a good friend of mine, someone that I met when I first started getting into Python a while ago, from San Diego Python, our local community. I have Brian Schrader here, and he's going to be giving us a discussion on Python multiprocessing. And I think that's a pretty big deal nowadays. I know with the change to Python 3.5, everyone is so excited about async IO. And I saw this guy the first time I met him. I think he was running like a multiprocessing test and jumping for joy because it failed. So I still don't understand how you can be excited for a failure, but at the same time, I'm sure he might get into that. So without further ado, Brian, the floor is yours.
Well, the reason you can be excited about a failure is at least it failed and didn't just do nothing, which is what it had been doing for me for weeks.
That's definitely true.
Anyway, as he said, my name is Brian, and I am a Python developer and bioinformatician. That means I work in bioinformatics. I just started working recently at the Scripps Research Institute, and I'll be talking to you guys about multitasking in Python, specifically the different types of multitasking and how you can accomplish each one. Multiprocessing is just one of those. So, without further ado, let me get my slides up here. Let's see. All right. So as I said, my name is Brian, and I look like this on the internet. You can find me there and at those places. And as I said, today I'll be talking to you guys about an intro to multitasking in Python. So the first thing we need to think about here is, like, what is multitasking? What do I mean by multitasking? Why should you use it? And how should you use it? So in order to go over this, we'll have to dive a little bit into how operating systems and processors work real quickly. I'm not an expert in either of those topics, so I'm just going to go over the broad strokes of what goes on. And then I've got a couple examples of how to do this in Python, as well as a bit of Java, C, and even Objective-C. So what is multitasking? Multitasking is really a pretty simple idea. It's how can we tell a computer to do more than one thing at once. Usually when you execute a program, the code will go line by line, doing one thing at once. When it finishes one thing, it will go to the next. Well, we might have cases where we want to do more than one thing at once. So we have like long-running updates, network requests, animations or UI updates, or lots and lots of really simple tasks that don't need to be waiting on each other. Like if you have 500 numbers, for example, and you need to add one to every one of them, doing them all in order you can, but there's no need because they're all independent of each other. And especially things like UI updates and network requests, if you have like an iPhone application and you are doing some nice animation on the screen and you try to do a network request in the background, well, the network request, the moment it starts requesting, is going to stop the animation. And that's not what you want. You want the animation to continue and the user to be able to scroll around while it's fetching data. And so that's an example of multitasking. So as I said, we'll do a quick diversion before we get to multiprocessing into a little bit about how processors work. As I said, I am not an expert. If you are, please forgive me. I'm about to butcher everything. So this is this is a cutout of Apple's A8 CPU. It's just what happens when they slice it in half and take an X-ray of it. It has 2 cores. You can see in the bottom right over here. Each core can do exactly one thing at once, and whenever it's waiting for something like disk, or whenever it's waiting for the network, or whenever it's waiting for really anything, it can switch between tasks. So it has like a long list of instructions, and says, oh, I'm waiting on this. Let's just do the next thing. And this is called preemptive multitasking. I'm not really going to do a whole lot of vocabulary, but it's just important to know. So using these cores effectively, using 2 of them effectively, is really important for performance software. As I said, CPUs spend a lot of time just basically waiting. The RAM, even RAM and memory, disks, the network, and all of these things take a lot of time to fetch data from. And modern operating systems can use this downtime. So how can we, as programmers, use this downtime? Because the processor can't predict everything, and there's a lot of code that we write that we could take advantage of this waiting time as well. One other thing is, now we'll take a quick diversion into like operating systems, as I said, real brief, because I'm not an expert in operating systems. Some real quick operating system terminology, a process. So a process is, you're probably familiar with them. They're the things you see in the task manager. So each row is a process. Programs run in what are called processes. Processes are isolated from each other, and they can't actually talk to each other without going through the kernel. So they have to go through the kernel in order to communicate. They are completely isolated otherwise. And that means they can't corrupt or mess with each other as well. But it also means they can't share data very easily. And one other thing to know about processes is that since they require their own memory, and since they're basically new instances of a program every time, they can take a while to start up and shut down. Now, what do I mean by that? So imagine if you have a box, and the box takes, like a voting box kind of thing. You slip an envelope in it, and that's an instruction. So every time you have to slip an envelope in it. And if you want to do more than one thing at once, well, get another box. And you can take twice as many envelopes. And so that's basically another process. There's a whole other box, basically. There's nothing you did to the first box to make it faster. You just got another one. And that can take a long time. You can imagine that in order to go get another box, you had to go dig it out of storage and put it on the table and maybe plug it in or something. And that takes a lot of time to start it up. And so basically, you can think of it that way. It's the same thing if you open up a terminal and you type Python, and then you go to another terminal and you type Python. You know they're not the same Python. They're two different instances of Python running. And this is basically the same thing. So as I said, this is a screenshot while I was making this talk of my activity monitor. And each one of these rows is a separate process. And as you can see, there's lots of them, and they're all completely independent. There's 326 of them, actually. So then the second thing, and the last thing we need to talk about operating systems is threads. Now, threads are a little different from processes. So first off, a thread exists inside of a process. And a thread can have a process can have multiple threads. So if we go back to that screenshot, you can see here, in each process, there's like the kernel task at the top has 112 threads. So that's how many individual threads belong to that one process. A thread is a section of code inside of a process that can be executed asynchronously. By default, every process has one thread, the main thread, where all normal computations are made. So when you run your code, it's running in the main thread of your process. And you can create new threads inside of that process. And since threads exist inside the process, the cool thing is they don't have the same memory limitations. They can talk to each other all they want. So you can have 112 threads all talking to each other. Now, this can cause a lot of very complex problems, like I'll get into later, but it also is a huge advantage because you don't have to do a lot of crazy workarounds in order to get them to talk to each other, because they can just do it by default. Another thing that threads have going for them is, unlike processes, they're very quick to start up and shut down. Since they're inside a process, they don't have to boot a whole new process to get going. And the CPU can switch between threads very easily and quickly, making them a nice, real quick, easy way to divide up your work. Now, you might be asking, like, what does this mean? Well, processes and threads are the foundations of multitasking. The different types of multitasking, which are much higher level than this, are built upon these two different things. And some of them use processes and some of them use threads. And it's important to know the difference between each in order to pick the one that's going to be right for you. So without further ado, let's get actually back to doing some multitasking. So personally, I learn by example. So I would like to actually show you some code samples instead of talking abstractly. I think I've done that enough. So we'll look at a couple different methods of solving a problem. So we'll look at the regular way, the serial way of just doing one thing after the other. We'll look at multitasking using threading and processes. So let's imagine you have a problem. You are tasked to build a program that fetches a bunch of articles from Wikipedia, around 1,000 articles from Wikipedia. So how would you do this? Well, if we have just the regular solution with no multitasking, it looks something like this. So you have, you import requests because it's the best library for Python web requests. You have your articles.txt file, and you read that in, and you get the list of links where each line is a separate link. And then you loop over the links, and you go get each link, and you get the response, and you save the text of the response to some list, and then do your post-processing. So whatever you need to do after that. So if we time this on the command line, we can see that it takes about almost 6 minutes to do 1,000 network requests on my work internet, which is pretty fast. So that's not really, it's a whole lot of time. I mean, it is a lot of web requests, but it's still a lot of time. So how can we make this faster? Well, first, I want to look at this. So this is the activity monitor running while I was waiting for this script to finish. And you can see it's only using 5% of the CPU. And it has, it spends a lot of time just sitting there. It's not really doing much of anything, except really waiting for Wikipedia to respond. You might notice real quick that it has 2 threads in the line. That is because requests, when you make a request, creates its own thread in the background. That's not really important to this, but if you were wondering. But yeah, so it's only using 5% because it's sitting there waiting all the time. So how can we make it not wait as much? Well, before we do that, I want to look into let's talk about waiting. As everybody knows, as Tom Petty once said, the waiting is the hardest part. So it's hard for humans to imagine like the levels that, or the amount of time relative that the CPU is seeing. So if we scale it up, for example, and we say 1 CPU cycle is 1 second, accessing main memory, the thing we all think of as really fast, takes 6 minutes. So even main memory really isn't that fast. I mean, accessing a solid state disk is 2 days in that scenario. That's a very long time for the CPU to basically just be sitting there. So every time it has to ask for data from the disk, it takes 2 days relative to what it's doing. And obviously, these are like blown up to the scale of 1 second, but it starts to give you a feel. And the moment you have to do a network request from even across the US, it becomes like extremely, extremely ludicrous how long the CPU is just sitting there. Also, these internet times are very optimistic because when I tried doing a ping from San Diego to New York City, it did not take 40 milliseconds. It took like 60 or 80. So it's almost double the time that you see here. So the CPU spends a lot of time waiting. And this is time you can use to do other things. So let's look at the first solution, which is using threads. So Python has a really great library for doing threading. And I'm actually going to be using it throughout this. So if we import the multiprocessing module and specifically a thread pool from it. A thread pool is basically, so there's 2 ways to go about making threads, and the same with processes. You can make them all manually. So you'd create one, give it a task, wait for it to finish, shut it down. And then if you wanted 14 threads, you'd have to do that 14 times. Or you can use a thread pool or a process pool, which basically you just say, I want 5 threads, and it creates 5 threads, manages them for you, waits for them, and shuts them down automatically. So really the thread pool and the process pool are the way to go because they're much easier. But it depends on what you're doing. If you are doing something that requires individual threads, then they are very useful. But since we're just doing a bunch of burst processing, I'm just going to use the thread pool. So just like before, we read in the file article.txt, and we define a function called doGet, which takes a link and gives you the text. So it goes out and does the request and comes back. And then we make a thread pool with 4 threads. And we say the app basically says for every link, call doGet on that link, and then divide that work into the 4 threads. So it basically, since we have 1,000 articles, it divides those 1,000 articles into 250 article groups, and then does the requests in four at a time. So inside that thread pool, go ahead.
Is there a particular reason why you chose 4 threads?
I did choose 4 because I have 4 CPUs in my. You could choose more. Usually for processes, at least, you want to choose. Going above the number of CPUs you actually have is fairly. The gain becomes less and less.
Okay.
With threads, I just wanted to be consistent with the processes. So that's the only difference for choosing 4. I could have spawned 1,000, but the problem that you have coming up is still going to be the same. So you could spawn lots and lots and lots of threads. And since they are fairly free to spawn, since they don't have their own memory and they share the same memory, they're actually a lot easier to spawn lots and lots of them. And if we look at how long this takes, it's about 1 minute and 43 seconds. So it's basically 3 times faster, right? So it's the CPU is sitting there doing more, and therefore gets it done faster. It's waiting for less and less things. So if we look at the CPU usage this time, it's a little bit better, right? So now we're at 40%, and we've got threads. You might be wondering how 2 threads for Python and requests plus 4 worker threads equals 9. But remember, those are the requests has to start up a thread for each worker thread. So that would be 2 per worker thread plus the main one, which no longer has requests. So that's 9. So at this point, it looks pretty good, right? The time went down, the CPU usage went up. We're using more of our computer. If we try the same with processes, now this code might look really familiar, but the difference is instead of importing a thread pool, we're just importing a pool, which it's a process pool, but Python doesn't call it a process pool. So as you can see, the code is exactly the same up until the bottom, where we make a new pool, which is a process pool with 4 independent processes, and we do the same thing. We say divide this work up between these 4 and do it. And now, if we look at the usage or the time, it takes pretty much the same amount of time, which actually kind of surprised me. But on average, it took about the same amount of time, which is kind of neat. But let's look at the usage, the CPU usage, and it looks a little bit different. So now you notice that instead of having a bunch of processes, it has, or a bunch of threads, it has a bunch of processes. So now there are, at the very bottom, there's the main process, which is basically sitting there waiting, so it's not using any CPU. And the process pool starts a bunch of threads to basically keep track of the different processes. So those 4 threads are actually keeping an eye on those 4 processes. And then you have the 4 workers above, which have 1 for requests and 1 for themselves. And they're each doing a decent amount of work. So we can see that I'm doing all these requests, and they're all asynchronous. So it's a little bit faster. And as I said, in the end result, your code is faster. And that's what you wanted, right? So we got everything to work. We got the code running using multitasking in 2 different ways, and it's much faster now. Now, the question is, why did it run faster? So because basically the code is spending a lot of time sitting there requesting and requesting and requesting and just waiting for what feels to it like years, we can tell it to do a bunch of requests at once. And when it does that, it can better use its time. The cool thing is, the threads basically say whenever there's downtime, it switches between a different thread. And processes is actually the operating system saying whenever it can divide up the processes among the CPUs. So the cool thing is threads and processes both run on different CPUs, but the processes are more independent, so they can actually do a little bit more work independently of the others. And so, go ahead.
So with that, are you I would say implying that depending on the amount of work that's needing to be done per, I don't want to say per process, but I guess in your function, is that the determining factor of where you start getting the diminishing returns of, like you said, for this one it was pretty simple, you got around the same time, but perhaps if your function was doing a little bit more, if you were doing more functions per thread or per processing pool, is that where you might see a difference?
So the difference actually comes depending on the kind of task that you're doing. In this case, we're doing something where it's just waiting for network requests. So they both basically function basically the same.
Okay.
When you're doing something that is more calculation-based, like as I said, the example of adding a bunch of numbers to things, or doing something that requires lots of CPU processing instead of just waiting for requests, there is a huge difference in which technique becomes more effective. The other thing to keep in mind is processes constantly, they require their own memory. So in order to use a process, which is more independent, you have to allocate that same amount of RAM. So if you're using Python and you're doing processes, a regular Python process requires 15 megabytes. So if you start up 15 processes, you now have 15 times 15 megabytes of RAM that is being used. Whereas if you have 15 threads in Python, you don't have that problem because they all use the same 15 megabytes. But specifically with Python, threading has one huge downside, which I will get into in a bit.
Okay.
So basically, it really depends on what you're doing, which is why it's really important to know the difference between the two. So now that we've kind of looked at an example, I want to do some more examples later. Quickly, I want to show you some samples of basically very similar code. It's not quite exact, but very similar code in some other languages because you may not be doing Python, or you may not be wanting to do Python. Most languages have the ability to do things like this. It's a fairly common thing, but they all have their ups and downs. They all have their goods and bads, and let's look at some of the code for making these happen. So if we look at Java, I used to program a lot in Java at work. So this is what I used to do for multi-threading. So at the top you can see there's an executor service. It's basically Java's version of a thread pool. And you just create a new one. And then you tell it to execute whatever your code is in the run block in a different thread. And then it will execute that, and it will go to the shutdown when it's done. So this is kind of like what it looks like if you're doing, if you're not using a pool in Python, you're doing it manually. This is almost exactly, we change the names, but it's almost exactly the code that you'd have to write in Python to do threads manually. I haven't used any sort of thread pools in Java, but I'm sure that they exist. As I said, the one nice thing about the Python module is that it takes care of all of this for you. So all you do is give it your code. If we look at something in Objective-C, which I'm not sure if anybody's familiar with, but this is the program you use to make iOS and Mac apps. It doesn't quite look like the other languages. Like the one in Java kind of had like the same almost feeling of Python, and then the Python one was very different than this. Technically, this is actually a C API, but it's only available on Apple's platform. So you have to be using C and Objective-C on a Mac or iPhone to be able to use this. But the first line right there, you can say dispatch async, and what this does is it says whatever is inside this function body, do it asynchronously. And the first parameter you give it is where you want it to do it asynchronously. So the operating system for macOS and iOS has a lot of different places you can say go do the work. So if you need it done right now, if you can have it done in a little bit, or you have it like a priority list or whatever. There's different ways you can do it. And so this dispatch get global queue is basically just saying use the default priority queue. So that's just whatever they use as the default. And then this funny looking caret paren void thing is an anonymous function. You can think of like a JavaScript anonymous function or like a lambda in Python. They're not quite the same thing, but it's close enough. And then inside where the comment is, you would do all of your code. So this says, go do whatever this thing is in that block between those red brackets. Do all of that on a different system somewhere. I don't really care where. And it will basically do that asynchronously. It's quite a lot less code than the Java version. It may be a little more complicated to start out with. I actually really prefer this because it is so there's so little cruft involved, just like the Python one, where there's very little cruft. And then if we look at good old C, everyone loves some C, apparently. I have actually never done threads in C. This is a bit of sample code from the web. But basically what you do is you create a thread handler right here, and then you come down and you give it something to do, which in this case is the do something function, and then you wait for them to finish. So it's basically like the Java version, except it looks a little more like C. And it has a lot less safety around it. The Java one will actually catch problems that happen, whereas the C one, as with many things in C, you're probably left to you're actually left to do most of the catching on your own, which can be good if that's what you need. But I can see, and you asked it earlier, what is the difference between doing, if both the multi-threading and multiprocessing took the same amount of time, they were both faster. That's actually should say 3 times faster than the normal case. Why would you use one over the other? And that's a really good question, and I kind of touched on it before, but the answer is basically context. Multitasking, which is the general term for all kinds of different multitasking, is very complex. And there isn't really a catch-all solution. So sometimes threads will be better, sometimes processes will be better. It really depends on what you're doing and the language and tools that you're using. Because, for example, in Python, you might think, I'll just use threads for everything. They have so many advantages. But Python's threads have a very key disadvantage to them, that where you would normally want to use threads, you have to use processes instead. Now, as I said, in our last example, the threading code used about 20 megabytes of memory, whereas the multiprocessing code used about 80 megabytes of memory, since each process needs its own complete copy of Python. So if you're RAM constrained, you definitely like threads better, which is actually why iOS uses them exclusively. Some good candidates for just multiprocessing in general: if you have lots of simple or lots of independent tasks, like as I said, if you have 2,000 numbers and you need to add 1 to each of them, that is it's a what they call trivially multitasked operation. They don't depend on each other at all. You can have 250 processes. Each of them adds 1 to a number and then returns. If there's no shared state, and what I mean by this is, like, if you have some global variable that your code relies on in order to do something, and the value of that variable is very important, if you do 2 things at once and one of them changes it and one of them goes to check it, the value might not be what you expected. And so it's best to eliminate that kind of thing when you're doing multiprocessing. Try to keep everything as self-contained as possible. One thing I've found, and this is just my opinion, the I/O-bound tasks, so things that are looking for network requests or disk or writing files or something like that, they're usually easier to multiprocess or multitask, like doing 1,000 requests to Wikipedia. CPU-bound tasks, like where you're adding those numbers, it can be a little bit harder because some languages, like Python, have some quirky behavior, and threading may not be what you need, and you might need processing, but if you have too many processes, you're using all your RAM. It's just important to think about the downsides and upsides to each one. So with that in mind, let's look at a couple more examples. And these are examples with maybe a non-obvious solution. It's going to look very similar, but the answer is not going to be what you'd expect. So the problem this time, instead of making a web request to fetch 1,000 versions of the Monty Python article on Wikipedia, you're going to build a program that takes a given number and sums all of the previous values. And I'll show you what that looks like. So basically, when you count, if we gave it the number 10, it would count 1, and then it would count 1, 2, and then it would count 1, 2, 3, then it would count 1, 2, 3, 4, each time going higher and higher until it got to 10. And I'm going to do these in a little bit different order. So let's cover the no multitasking case first, just how you would do this normally. So we have a simple loop. We have a value that equals 0. We loop over the number that we're given. We loop over every number that that gives, and then we add that a value. So as I said, this goes 1, 2, 3, 1, 2, 3, 4, 1, 2, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, etc. And then we'll give it some fairly high numbers so that it can, actually take some time. And the entire point of this is just to be something that's fairly CPU intensive. So there's almost no time that the CPU can pause and wait around. So if we look at the CPU usage for this case where there's no multitasking, it takes about 19 seconds. So, that's a good benchmark. Now we can use that 19 seconds. Now what does the CPU look like? Well, it looks like what you'd expect. I said there was no time for resting, and it's maxing out. So the CPU is going for those 19 seconds at full capacity. It's maxing out one thread on one core of my processor. So if we look at the version with processes this time, so as I said, we just make a little process pool up at the bottom, just like we did before. We give it an array of numbers, and we say for each number, call do something on it, and divide that work between the processes. So this is going to take those 5. It's going to give 1 to each, and then one unlucky process will be given 2. And then each process will go about and do its thing and count to this outrageously large number. And if we look at how long that takes, you're looking at something like 13 seconds. So it's not quite as big of a jump as last time. Last time we got a third of the performance increase, and this time it didn't even cut it in half. So that's already something that's very interesting. If we look at the CPUs, you can see that this time, actually, since one of those numbers, if I go back real quick, the 1,000 number finishes so quickly, I couldn't actually screenshot it fast enough. So the second to last thread was running at full speed, but I couldn't screenshot it fast enough. And then the very bottom one is the main, or the one with 4 threads is the watcher, and the one with 0 is shutting down. But you can see that a lot of these processes are, they're working very hard to do your code, and they're maxing out all my CPU. If you look at the graph down here, the CPU load, they're like maxing it out to do this work. If we take a look at the threading version, we just change out the pool for a thread pool, right? Everything looks fine. But remember that I talked about a catch, because there's always a catch. And this time, if you do exactly the same thing, but with a thread pool, it takes 20 seconds. So the regular case took 19 seconds. So this is actually slower, on average, than the regular serial version. And this is what I talked about. This is where we have a catch. Now, why did this happen? Why did this happen? If you look, the entire time my CPU is using 100%. Like, why is it taking so much more time? Well, as I said, Python does threads a little bit differently. So this is a very complicated topic. I'm not going to go into it a whole lot. If you want to know more about it, David Beasley, he's a longtime Python guru. He has given many talks about Python and threading, and I definitely recommend you check his out. He explains it far better than I ever could. But basically, the short version is that Python threads are just like regular operating system threads, but unlike real operating system threads, they can only execute one thing at a time. So if you have 100 threads and they all want to add one to a number, Python will say, thread number 1, what do you want to do? Thread number 2, what do you want to do? Thread number 3. They can't all go at the same time. They have to wait for each other, which is really not threading anymore. It's doing things in order. But if you're doing something like what we were doing before, where you were waiting all the time, the C will say, Python, or thread number 1, what do you want to do? And it says, I'm waiting, and then it moves on, right? But if every thread wants to do something right now, it actually can't handle that. So it starts to switch really quickly back and forth, and that switching isn't free. That switching costs a lot of time, and as you can see, it made everything slower. So in Python, CPU-bound tasks using threading are slower. As I said, this is very specific to Python. This is not a factor in other languages like the Java or C or Objective-C versions. They do not have this problem. This is a specific version of C Python that has this problem. And it is there, and it has been there for 20 years. So I don't know if it's going away. There's been a lot of debate on this problem. It's very complicated. But this just shows that it really pays to be familiar with what you're doing. So the tools that you use really, really have an impact on how you use them. So in Python, threading is not usually the way to go when you're doing CPU-bound things. If you're doing a lot of I/O, like network requests, or if you're making a web server to respond to requests, then threading will be fine because you spend most of your time waiting. But if you're doing calculation, it can make actually everything worse. Real quick, I want to cover some other types of multitasking. I'm not going to go into much depth on these. But if you've ever heard of these terms, one of them is called coroutines. A coroutine is basically a fancy way of doing what looks to be threading, but in only one thread. So basically, you can think of coroutines as code that is nice to its neighbors. So functions, when you write them, can pause. So the function will say, I am done now. You can go and do something else for a while. So this is good if you're answering like web requests. So somebody makes a request to your website. They want their username. So you say, OK, let me go to the database. And the database says, hold on. And then it has to go get the thing that you want, which, as we saw, can take years relative to the CPU. And so what the function says is, all right, I'm waiting for the database. I'm pausing right now. And then the server can go do something else. So it will say, OK, this function has given up control. I will go do something else. And then usually that one will give up control. And it will basically just switch between these various coroutines, which are fancy names for functions that are nice to each other. And it will basically figure out how to run them. So it's one thread, one process. But if it involves a lot of waiting, then it's very popular. So like Python's G-event, I don't know if you've ever heard of G-event, it's a fantastic library for doing this. Or the new async syntax in Python 3.5, it uses coroutines. And so they're very popular in Python. They're actually the preferred way of doing what you would normally do in threading in Python, because threading doesn't work the way people think it does. So the other thing would be asynchronous functions. Once again, everything is in a single thread. But every function is treated as asynchronous. So every function call is treated as a pause point. Basically, there's no such thing as synchronous code. So every time you call a function, the program could choose to go do something else at that time instead of answering your function. An example of this is JavaScript. Every function in JavaScript is asynchronous. So if you try to call a function and then do something afterward, that function might not actually have been called yet. It might have said, OK, I'll do that in a bit. Basically, it treats everything as a to-do list instead of actually doing them. And this can be tricky to get used to, but it's actually one of the things that makes JavaScript very powerful, because it can do a lot of things very quickly if a lot of those things are waiting. So this is another solution to the problem of I'm constantly waiting for everything. Some stuff I didn't cover, which basically is a lot of the complications that come with multitasking. So when you're using threading, where everything has the same memory, you run into problem with semaphores and locks and race conditions. and this is all the like the scary names that you hear when you do multiprocessing. If you do it right, most of the time you don't need to do any of these. I've never touched in any multiprocessing code that I've ever had to write a lock or a semaphore or encountered a race condition if I've done it right. That's the good news, because most of the time when you need to start dealing with these, I mean, there are definitely occasions where you will need semaphores and locks. But if you do need to encounter them, you need to seriously think about what you're doing and can you do it a little bit differently, because you get into a world of hurt when you start dealing with this stuff. It becomes very, very painful. And generally, for most things, not worth it. So definitely, if you encounter these, it's definitely good to look into and definitely good to understand, but seriously consider what you're doing when you run into them. So basically, the summary of this is multitasking, when it's done right, can be really, really helpful. We got those Wikipedia articles, all 1,000 of them, instead of in 6 minutes, in 2, which is really good. But when it's done wrong, or done when the programmer doesn't really know the outcome or what they're expecting, it can be very disastrous. It can be a huge problem. But as I said, that's all being familiar with your tools. So the next step really is to go out there and do it. I mean, there's lots of great tools for doing multiprocessing. Python has some really amazing tools. Everything you saw for my Python code was Python 3. I highly recommend, if you're doing multiprocessing, to do it in Python 3, because it's just much easier. The whole syntax of doing with pool that I showed, which is 2 lines, is not available in Python 1 or Python 2. So I definitely recommend using Python 3 for that. It's much easier than doing it manually.
And Guido said so.
Yeah, and you should be using Python 3, period, because you should be using Python 3. As I said, my name is Brian Schrader. You can find me here, and I look like that. Yeah, so if, I talk about multiprocessing a lot on my blog, mostly because I keep running into it. You can find me on Twitter. If you like Twitter, I like it a lot. You can talk to me there. And yeah, that's it.
Awesome, Brian. That was absolutely amazing, actually. And you've known, like, the big projects that I've always worked on have been web scraping projects. So for me, I've been looking at ways that I can speed up that process. I think the big project, the one that we actually we were introduced, together on, was my podcast aggregating project.
Yes.
I think
I'm still waiting on.
So right now it's taking a hiatus, but I might have to bring it back out. I was actually able to start pulling channels at like entire networks, but
Nice.
The problem was it was pulling like 13,000 links in like 6 minutes, and so if I can, which is good, but at the same time, if I could bring that down to like 3 minutes, I would be much happier.
Definitely.
So I think I'm definitely going to be looking at some of my existing scraping projects and see how I can implement some of the multi-threading and multiprocessing in that, so I can jump up and down when my tests fail as well.
Yeah,
so.
There you go. It's always an exciting thing, but. As I said, I would definitely recommend using something like G-Event. It makes everything so easy.
Okay.
And it makes everything very easy to do as well. Like you might want to spawn all the requests at once, but then usually G-Event is just easier.
Well, cool. Question: what projects are you working on?
I have a couple. Right now, I'm working on so I was working on an internet enabled coffee pot that would allow you to communicate with it and brew coffee via a joke protocol from 1998. Because apparently that's what I spend my time doing, is building joke protocols. Now that is pretty much done, I am working on a project called Adventurers Codex with 2 friends. It's a web app for managing characters in tabletop RPGs like D&D or Shadowrun or something like that. And so we're basically trying to take some of the annoying things of playing D&D on paper in the year 2015 and bring the game into 2015 without losing all of the cool stuff like rolling dice and things like that. So we're trying to keep it authentic but still provide some nice features.
Well, if you need someone to help test that, give me a call. I'd
I do.
absolutely love to jump into
And
that.
actually, if anyone out there wants to help test, give me talk to me on Twitter. I would definitely appreciate it. We do need testers. We are nearing a phase where we can actually have testers.
Nice. Well, all right, everyone, and that was another Saturday discussion. I'd like to remind you that Code Newbie does have things for all programmers, not just Python developers. We actually have our Ruby Monday, as well as on Thursdays we have a Python Thursday group and our JavaScript enabled group. And don't forget our world famous Twitter chat held on Wednesday nights at 6 o'clock, where we talk about different topics in tech. And I hope that you guys enjoyed the show and get ready for next week where we cover APIs in Ruby. So with that, have a good day.
Sweet.